So far we have learned basically how to do differentiation of algebraic functions related to the power of x to the power n differentiation type of applications, along with all the properties and all, as we have seen already. Okay.
So
Now we'll move
that
on
in
to
worksheet 2 we were left with question number.
Sorry, in worksheet 2 what happened?
We were left with question number 5.
Question number 5. Yes, I'll explain that to you. So we have completed up to question 4 all the parts, right?
Yes.
Yes,
Yes,
sir.
sir.
Okay. Okay, so we will start today with the discussion of that question number 5, which was quite an interesting question, but needed a bit of application. So worksheet number 2, question 5. So I'm just putting the data of the question over here. Just give me a moment. So I think some derivative of the function was given and some other condition was given, right? Yes, so it was given that y is a polynomial function of x, okay, such that so in general, what is a polynomial function? A polynomial function is one which is written as a power series, like some constant term plus another constant into x plus another constant into x square plus this kind of series going up to nth power of x. So this is called a polynomial of degree n. For example, if the value of n is 3, then we call it a cubic function, which is a subset of polynomial functions. If the degree is 2, we call it a quadratic function, and so on and so forth. So now here, in addition to this information that y is a polynomial function of x, it is also given to us that dy by dx, the value of the derivative or the differentiation of y with respect to x, that is given to us as ax square plus bx plus c, where obviously a, b, and c are constants, okay, such that y is equal to 0 for x equal to 0. Then y is equal to 6 for x equal to 1. Y is equal to 0 for x equal to minus 1. And in addition to this, dy by dx's value is equal to 2 for x equal to 0. So this is like 4 separate pieces of information are given to us. These 4 statements, they are 4 separate pieces of mathematical information. In addition to the fact that y is a polynomial function of x and dy by dx is of this type, where a, b, c are unknown quantities. So we have to calculate the values of a, b, and c and find. Okay. All right. So now this is, as I said, a slightly more conceptual type of question. So first thing we have to understand that when we differentiate any term which has x to the power n, what happens to the power? It becomes 1 less, right? This becomes n minus 1. So if y is a polynomial function of degree n, what can we say about dy by dx? Can anybody tell me that? If y is a polynomial of degree n, what does that say about dy by dx? What kind of term dy by dx will be?
Linear equation.
See, linear kab hoga when the maximum power is square, na? But what about if the maximum power is cube?
Oh, sorry. तो इधर क्यों होगा?
So linear is when maximum power is 1.
No, that is a linear function, but I'm saying dy by dx. When is dy by dx linear?
Square,
When y is a quadratic function, na? Understood, na?
Sorry.
So for example, suppose y is linear. Y is, let's say, 2x plus 3. This is an example of a linear function. So what happens to dy by dx here? It's just 2. So it's not got any power of x. So the degree of this is n equal to 0. because the degree of this one was n equal to 1. Okay, now another example, suppose y is a quadratic function, is x square plus 3x plus 2 something like that. Then what about dy by dx over here? It is
Linear.
becoming, yeah, it's becoming linear. So its degree is becoming 1 because y's degree was 2. So like that, in general, if I say if y's degree is n, okay, then what about dy by dx's degree? It will become n minus 1.
N minus 1.
So this will be a polynomial of degree n minus 1. This is the general rule. Na? So now apply that over here. So here what is happening? You can see that dy by dx is basically what? It's got a it's a polynomial of degree 2. Okay. Its degree is 2. So then what we can say about y? Y must be a polynomial of degree
3.
3. Okay. So we can start with that. So let us start with assume y is equal to, let's say, some px cube plus qx square plus rx plus s, where p, q, r, s, they are unknown constants. So there are some numerical constants which are unknown to us. So this statement would make sense. Okay, that because this is a polynomial, because dy by dx is a polynomial of degree 2, so that means y must be a polynomial of degree 3. So this is what we are saying, that dy by dx is quadratic. So this implies that y must be a cubic function. The cubic function means its degree is 3. Quadratic means that its degree is 2. So we can start with this assumption. So now we have 4 unknown quantities, and for that we need 4 information to find out 4 unknown quantities. So these are the 4 pieces of information. Okay. These 4 pieces of information, 1, 2, 3, and 4. We will have to make use of these 4 informations to find out the unknown quantities PQRS. And once we know the unknown quantities PQRS, from that we can find out the quantities ABC also, because they are after all linked to each other. Because if y is known, then obviously dy by dx we can find out. People, are you understanding what I'm saying over here?
So
Yes,
that
sir.
x value we can't put in that ax square.
We can't put what, beta?
So that is the general formula, no? Standard formula of one ax square plus bx plus c.
No, it's not a standard formula as such, no, but dy by dx is given as a quadratic function. So it's a particular case now. When is dy by dx quadratic? When y is cubic, no? You understanding, no?
Yes, yes.
For example, if y had itself been a quadratic function, then dy by dx would not be quadratic, no? It would be linear.
Yes, sir. Understand.
And moreover, in this ABC are unknown quantities, no? We don't know their values. We have to calculate them. Okay. So that means we have to somehow fit this information that is given, that y is 0 for x equal to 0. Then the second information given is that y is 6 for x equal to 1. All this has to be fit into some relation between y and x, so that we can then find the unknown quantities. You understanding the point? Okay. So see,
Yes,
we
sir,
have
yes.
4 unknown quantities, 1, 2, 3, 4, and we have 4 information given to us. So we have enough conditions given. Now it's just a matter of substituting. So if I've assumed y is like this, then what will be the value of y when x is 0? Okay, so let's use the first thing, that y should be 0 when x is 0. So which equation I'll substitute in this equation, because this is the relation between y and x. So 0 should be equal to p into 0, okay, plus q into 0 plus r into 0 plus s. So what this is telling me, that s's value is 0. So the first of the 4 unknown quantities I have got. Okay. Then similarly use the
So
second.
we are writing. Can you wait?
Yeah. So this is how you have to proceed actually. So just like I have substituted the first condition here, like that you yourself substitute the second, third, and fourth condition also, and try to
Okay,
find out
sir.
the unknown quantities. Okay.
Sir, I think if we solve this question with integration, it will become easier.
Sorry, beta, I couldn't hear you. A little louder, please.
Yes, sir. Sir, I'm saying that if we solve it with integration, it will become easier.
But like, see, as of now, we have not learned integration. Na? So we will
Okay.
stick to, even this way it is quite easy, na? Because it's only polynomial function. So there's not much to do. You understand? Na?
Yes, sir.
Integration में क्या करेंगे? We'll take this dy by dx and integrate it. Now instead I'm saying take y as this and differentiate it. So it's just the reverse step of that. No?
Yes, sir.
So because ultimately it's a polynomial function of degree 3, so it's not so difficult to do by this method also. It's reasonably easy. Of course, we will see integration very soon, and we'll see how to solve situations like this using integration also. If you're familiar with integration from before, then you can go ahead and use integration. Okay, that will save you 1 or 2 steps, no doubt. Okay, but as of now, I will be solving this by using differentiation. So I'll go in like a reverse order. Okay, so now see, like I have substituted here to get this first equation, which is telling me s is 0. Like that, what will you get when you substitute the second condition over here? So let's see that. So y should be equal to 6 for x equal to 1. So in this equation, in this PQRS equation, substitute the left hand side, that is a value of y, as 6. In the right hand side, substitute x as 1. So p into 1, right, plus q into 1 again, plus r into 1, and s is already 0, so I'm not substituting this because I've already taken s as 0. So this should be 6. So what equation this is telling me? That p plus q plus r, the sum of these three terms, is equal to 6. So this doesn't directly give me the values of p, q, r, but it gives me more information. Okay? Now let's go one step further. Let's substitute the third thing. Okay, that is given to us that y is again 0, but this time for x equal to -1. So let's substitute in this equation again. Okay. So left hand side is 0, right hand side I have to substitute x as -1. So this will become p into -1, because -1 cube is -1, but q into 1, because -1 squared is 1, okay, plus r into again -1. So now you see one more useful information I'm getting, that minus p plus q minus r is equal to 0. You can see that already if I compare these two equations, I'll get one more variable. If I just add these two equations, p plus q plus r is equal to 6 and minus p plus q minus r is equal to 0. So if I just add these two, I get 2q is equal to 6. So I'm getting one more piece of information, that q is equal to 3. So I've got s so far, I've got q so far. Now just remaining are p and r. So for that I will use another term which is given. Now the other term that is given, notice, is this, that dy by dx is 2 for x equal to 0. So this is equal to 2 for x equal to 0. Now see what we have taken as y. Since we have taken y as px cube plus qx square plus rx, okay, where already we have taken s as 0, but q's value is also 3. So according to our assumption, now what is dy by dx? Dy by dx is differentiation of this term. So that is 3p into x square plus 2q into x plus r. Okay. So this is our value of dy by dx. We'll compare it with ABC again, but this is our value of dy by dx. So now when we substitute this information, we have to substitute it here. So left hand side dy by dx is 2, right hand side x is 0. So this now tells me that r is equal to 2. So I've got s, I've got q, I've got r. And now if I substitute the value of q and r in one of the earlier equations, I'll get the value of p also. So you can see from this equation, p is equal to q minus r, right? So q is 3 and r is 2. That means p's value is 1. So now I've got all the unknowns. Okay. So I've got p, q and r and s. So I know that y is equal to px cube. So that's x cube. Okay, plus qx square. Now q's value was how much now? 3. Okay. Plus rx. So r's value is how much now? R's value is 2 and s is 0. And from this, I can also see that dy by dx is 3x squared plus 6x plus 2, which is supposed to be ax squared plus bx plus c. So comparing both the sides, you also get the value of a as 3, b as 6, and c as 2. So you're getting y as a function of x, and we are also getting the values of a, b, and c. Okay.
So we were
Yes.
about to write.
Yes, beta. So again, you can see that the actual application of differentiation is very simple here. It's just differentiating x to the power n type of terms. But along with that, we are using algebra and having to substitute given conditions in algebraic equations to find unknown quantities, simultaneous equations for p, q, r, etc. Purpose of this kind of test is just to, this kind of question is just to increase your solving ability a little bit, okay. Your ability to handle equations.
Done, sir.
Okay, understood this now?
Sir, could you
Yes,
just
sir.
scroll the slide a bit up? As
Yeah,
it is.
sure, just a minute.
Yes, sir, just a minute.
Yeah, I'll go back just a minute. This part, no?
Yes, sir. Just a minute.
Okay.
Yes, sir. Thank you.
Okay. All right. So as I said, let's continue ahead with more about differentiation, more types of functions. So in the fourth lecture, we had seen a little bit about differentiation of trigonometric functions, sine and cos. So I will take you a little bit further in that. Okay. So we'll also discuss a little bit about the sine and cos functions in four quadrants. Okay. You people have done components of vectors, na, in 2 dimensions, I cap, j cap.
Yes,
Yes,
sir.
sir.
Yes,
So a
sir.
little bit familiar with sine and cos in four quadrants like ASTC rule.
Yes, sir.
Yes, sir.
Yes,
Yes.
sir.
So we'll do a bit of review of that and understand that in relation of this also. Okay. So trigonometric functions and their derivatives. So last time when we were discussing sine and cos, we had just seen the values of x between 0 and 90 degrees. Okay. Now we will see in all four quadrants like that. We'll understand sine and cos as continuous functions for which x can take any value from minus to plus infinity. Okay. So let's start with the simple sine function. And this is very important to understand because later in physics, when we come to topics like oscillations and waves, etc., sine functions are very important in the mathematical side of that. So, okay. So y is equal to sine x is this function where x can be any real number. That is x going from minus infinity to infinity. Okay. So the value of sine x works in such a way that if we plot sine x versus x, we get this kind of a shape. For the fundamental cycle of one rotation or 2 pi radians, okay, we get this kind of a cycle where the value of sine x increases from 0 to 1 as x goes from 0 to pi by 2, then again comes back to 0 as x goes to pi, then it goes to minus 1 as x goes to 3 pi by 2, and finally comes back to 0. And thereafter what happens is that this repeats itself. So this graph, it keeps on going like this. So each cycle of 2 pi is the same. So what's happening from 0 to 2 pi, the same thing is happening from 2 pi to 4 pi. The same thing is happening from 4 pi to 6 pi. And similarly, even before that, the same thing is happening. So this graph is what we call a continuously periodic graph. So sine x is a periodic function, okay, with a fundamental cycle of 2 pi. 2 pi is the same thing as 360 degrees. So of course, you should also remember this conversion that pi radians is equivalent to 180 degrees. And radians is the what we call the standard international or SI unit of angle. So basically, in mathematics or in geometry, we define angle as the ratio of an arc to radius. So if we rotate a radius to an angle theta, then the arc length it cuts, that is such that, so when we express it this way, the value of theta that we get is in radians. So that is why you can see that when we cut a quarter circular arc, the arc length that we get, let's say S1 in this case, is a quarter circular arc. So it is from this formula you can see theta is equal to pi by 2. So it is pi r by 2. Similarly, when we cut a semicircular arc, so this angle here becomes what we call pi in radians. Then the arc length that we get is pi r, this half circle. This is quarter circle. If we take an arbitrary example, like let's say we have cut an arc of 60 degrees. So for example, here if theta is equal to pi by 3, so pi by 3 radians is the same thing as 60 degrees. Then the arc length that we get, then S will become pi r by 3, which you can see is 1/6 of a full circle. Okay. So why it is 1/6? Because it is 1/6 of a full circle, because theta equal to pi by 3 is 1/6 of 2 pi, one circle. Okay, so it works in ratio and proportionality. So this angle of 90 you can say is 1/4 of a full circle. So the quarter circular arc is 1/4 of 2 pi r. Okay. So here S1 is 1/4 of 2 pi r. Here S2 is 1/2 of 2 pi r. So likewise, in this case above, where the angle we have taken is 60 degrees or pi by 3, you can see that the arc length is 1/6 of 2 pi r. Okay. So that's in general about angle in radians. Now coming back to sine. Sine has this very interesting property, the sine function.
Sir, can you wait?
That is,
I'm still writing the graph. Sir, I'm still writing.
okay. Okay, so you can write down this part first, then we'll come to the sine functions properties.
Yes.
Sir, is it compulsory to draw the graph as well?
Sorry, come again, beta.
Should we draw the graph as well, or only the note is?
Yeah, draw the graph of sin x also.
Sir,
Yes.
you wrote a statement with note sin x, periodic function with a fundamental cycle to pi. Can
Yeah,
you please
sin x is a
explain that?
periodic function. So periodic function means it keeps repeating itself.
Okay, sir.
And it's a repetitive function. And the fundamental cycle is 2 pi or 360 degrees. Now we're going to understand that using vectors also how it happens actually, using projection of vectors. But here in the graph you can see that the wave shape of the sine graph is such that one wavelength or one cycle is 0 to 2 pi. Then between 2 pi and 4 pi, it's a repetition of the same wave. Then 4 pi to 6 pi, or similarly minus 2 pi to 0, it's a repetition of that same wave, right? So understood this point now about periodic nature?
Yes, sir.
Yeah.
Yes, sir. Please wait.
So can you please repeat what you said about the graph?
Yeah, the graph is repetitive. It's like it's a wave shape which has a fundamental cycle of 2 pi, and then that cycle repeats itself. So you can see that shape, na, that crest and trough. So that pair of crest and trough that is between 0 and 2 pi, that repeats indefinitely, na, from 2 pi to 4 pi, 4 pi to 6 pi, like that. So that is what we mean by saying that it's a periodic graph.
Okay, sir.
Sir, in semicircle, the theta, what is the value?
Theta is pi, beta, half of a full circle. So 2 pi corresponds to 360. So semicircle is 180, which corresponds to pi.
Yes.
So pi is such a number that it is actually the ratio of the arc to radius for a semicircle, or 2 times pi is the ratio of the circumference to radius for any circle. So that's an interesting fact of Euclidean geometry, that it doesn't matter what what size of circle we draw, whether the radius is 2 centimeters or 2 kilometers. The ratio of the circumference to radius, that ratio will always be a fixed value, and that value is 2 pi. Or if we draw semicircles, that ratio of arc length to radius will always be a fixed value, which is pi. So that is the significance of the number pi in mathematics and in geometry. That is the significance of the number pi.
Done, sir.
Sir, 1 second.
Yeah. Okay, done.
Yes, sir.
Okay. Now see, what we are going to do is we are going to correlate what you have learned in 9th, 10th about trigonometry, that is, trigonometric ratios of a right angle triangle, with respect to what you've recently learned in vectors about components of projection of a vector in 2 dimensions. That is, any vector in 2 dimensions can be written as some x component times I cap plus some y component times j cap. So we will correlate these two things, and through that correlation, we will understand how to extend the idea of sine and cos from values between 0 and 90 degrees to more than that. Okay? So if we talk about trigonometric ratios, this is different to trigonometric functions. So if we talk about trigonometric ratios, for obviously this applies to for a right angle triangle. So a lot of this will be repetition of information for you, especially for math students and all. It will be a repetition of what you are aware of from long time, but still there's a value in seeing this. Okay, so we're doing this in detail. So if you take any right angle triangle, okay, it turns out that the ratio of the sides depends on the angles. For example, if this angle is theta, this angle is 90 degrees minus theta. Okay. And if we are taking theta as our reference angle, then opposite to theta, the side length is called the perpendicular. Same side as theta is called the base. And the third one is called the hypotenuse. So as you know, trigonometrically we define sine theta as perpendicular upon hypotenuse. We define cos theta as base upon hypotenuse, and we define tan theta as perpendicular upon base. Okay. And to that extent, you can directly see from here that sine of 90 minus theta. So if you take this as your reference now, this as your reference, then this is the opposite side now. So it will become b upon h. So that is the same thing as cos theta. So we have this identity that sine of 90 minus theta is cos theta, or we can also write it as sine of pi by 2 minus theta is equal to cos theta. And similarly, you can also see for this angle, the cos will be same side, that is p divided by h. So cos of 90 degrees minus theta will be equal to p by h, which is also sine theta. So we have this other identity that cos of pi by 2 minus theta is equal to sine theta. And similarly, there's one for cot also, but I'm not getting into that. That's not too important. Okay. Now, the standard examples that you need to keep in mind of right angle triangles. Which will be very useful for you in, physics, vectors, kinematics, all sorts of chapters like this. So three particular triangles you need to keep in mind. One is the 30-60-90 triangle. Okay. The other is the 45-45-90 triangle, or the isosceles right angle triangle. And another one is something which you might not have seen earlier in 9-10th, which is the 3-4-5 triangle, or the 37 degrees, 53 degrees, 90-degree triangle. So what you need to keep in mind is that these triangles have particular shapes. So if this angle is 30 degrees and this angle is 60 degrees, then these will be in the ratio x root 3x and 2x. Whereas if these two angles are same, 45 degrees and 45 degrees, these two sides will be the same. And this side will be root 2 times this. Whereas if this angle is 37 degrees, so this angle becomes 53 degrees, then these will be in the ratio 3x is to 4x is to 5x. Okay. So if you just remember the geometry of these triangles, then you will never forget the values, that sine 30 is the same thing as cos 60 is equal to 1 by 2. Okay. And sine 60 is the same thing as cos 30, which is root 3 by 2. And tan 30 is the same thing as cot 60 is equal to 1 by root 3. Whereas here you will remember that sine 45 is the same thing as cos 45 is equal to 1 by root 2. And tan 45 is the same thing as cot 45 is equal to 1. And now particularly useful in physics is this third type of triangle for us, that sine of 37 is the exact same value as cos of 53 degrees, which is equal to 3 by 5. And cos of, or rather sine of 53 is the same thing as cos of 37 is equal to 4 by 5, right? And tan 37 is the same thing as cot 53 is equal to 3 by 5. So these are absolute things that you must remember. Like, I'm especially talking about students of NEET over here who are not doing trigonometry in maths. So as part of your physics knowledge, both from the vectors as well as the calculus chapter point of view, these triangles you should not have to think twice about, all these values. So rather than memorize them as tables and all that, I would advise you to just keep in mind these three triangles and the ratio of the sides. So accordingly, you can always work out the value sine 30, cos 30, sine 45, etc. So So these are some standard examples of right angle triangles. Of course, these are not the only possible right angle triangles. There are infinite number of right angle triangles
Sir.
possible. Yes.
Sir, in the second triangle, sine 45 degree is equals to cos 45 degree. After that,
Yes.
what we wrote?
Because it's an isosceles triangle, na beta. So the value of the perpendicular is the same as the value of the base. Na?
Yes,
Understood?
sir.
That's why it comes out
Yeah,
1 by
okay.
root 2. Because if the two sides are equal, then the hypotenuse will be root 2 times that using Pythagoras theorem, right?
Okay, sir. Thank you, sir. So can we write?
Yeah, you can write this down. Okay. Also, obviously, like I'm assuming all of you are familiar with this, but in addition, you should always remember that any right angle triangle, there is one very fundamental principle which is Pythagoras theorem. Okay. I'm sure.
Sir, can you minimize the screen?
Yeah. So I'm sure most of you know how to prove Pythagoras theorem also. There are many interesting proofs historically of how Pythagoras theorem was established, how it was proved. So long before algebra was invented and all that, right from the time of Greeks and all that. Okay. So if you just have these three triangles visually in your mind, the 30, 60, 90 triangle, the isosceles right angle triangle, and the 37, 45, 90 triangle, sorry, 37, 53, 90 triangle. Okay. Then you will not have difficulty remembering these values because you will have to remember these values for solving questions. Whether they are questions related to vectors or they are questions related to later chapters in physics like Newton's laws, etc. Or even in calculus, we will see there will be questions where we have to relate these things. So this is an absolute must. You must remember these values which I've written over here. Okay, so these are done.
No, sir. Last two triangles.
Okay, okay.
Yes, sir. Done.
Done, sir.
Okay, so done now, people?
Yes,
Yes,
sir.
sir.
Okay.
No.
So now see, from this idea of, what we know from before about right angle triangles and trigonometric ratios, not only that, some standard values over here. Now, next thing we move on to, of course, you should also keep in mind that how to express these in radians. This is pi by 6, okay? 60 degrees is pi by 3, of course, and 45 degrees is pi by 4. Now, the next thing is we will understand sine and cos in terms of components of a vector. Okay? Sine theta and cos theta in components of a vector when we express it in two-dimensional system. So, of course, this will help a lot that you're already familiar with vectors to a very large extent. So, as you know, if we draw a vector in reference to a xy coordinate system, that means in reference to a two-dimensional rectangular coordinate system, then we can draw it in such a way that it is represented by an arrow, okay, starting from the origin, having a particular length which represents the magnitude of the vector, and having a particular direction in which the arrow points, which represents the direction of the vector. Now we can always express it. So if this arrow is making an angle theta with the x-axis, then we can always express the vector A itself as if it is the sum of two other vectors. And those vectors are actually lying along the x-axis and the y-axis respectively. So we can express this vector A as the sum of these two, what we call the components. So that can be written with subscript AX and subscript AY. And as you know, we write the unit vector along the x-axis as I cap, the unit vector along the y-axis as j cap, unit vector along the negative x-axis therefore becomes minus I cap, unit vector along the negative y-axis becomes minus j cap. So in component form, we write the vector A as AX I cap plus AY j cap. But as you can see, applying trigonometry over here, this is a right angle triangle. So to this right angle triangle, if you apply trigonometry, you can see that, and this is of course magnitude of the vector, the hypotenuse. So AX upon mod A becomes perpendicular upon hypotenuse, so it becomes sine theta. Sorry, it becomes base upon hypotenuse. So this is equal to the base upon the hypotenuse. So that becomes cos theta. And AY upon mod A, that becomes the perpendicular divided by the hypotenuse. So that becomes sine theta. So then we have a different way of relating this. This is a new way of relating cos theta and sine theta. So what that also means that if I just consider for a vector of unit magnitude, it means magnitude equal to 1. If mod A is equal to 1, then its x component is cos theta and its y component is sine theta. Okay. So this becomes a new way of understanding what is cos theta and sine theta. Cos theta is the x component of a vector of magnitude 1 at an angle theta to the x-axis, and sine theta is the y component of a vector of magnitude 1 at an angle theta to the x-axis. Okay, so just make a note of this diagram if you like, and we will discuss
Yes,
now.
sir,
We'll
can
see
you please wait?
Yeah. Next, we will discuss how this approach to understanding sine theta and cos theta. This helps us understand sine and cos in 4 quadrants. This is
So you have written ax equals to a cos theta, like a is magnitude of a, right?
yes.
Okay, sir.
Here we are understanding that capital A is a short form for this also, right? Magnitude of the vector.
Done, sir.
Sir, 1 minute.
Sir, wait.
Yeah.
Sir, completed.
Sir, 1 minute. Last line.
Yeah. Right, done now?
Yes, sir.
Yes, sir.
Okay. So now that we have understood that sine and cos can also be thought of as components of a vector of magnitude 1, as it is, rotated through an angle theta. So we can visualize the way sine and cos behave as we change the angle. Okay. So let's say this circle is just to help us make the diagram, but let's say this is a circle of magnitude or radius 1. So any vector that I draw which represents one of the radii of this circle will be a unit vector. Okay. So now talking about our original vector, if we place it at theta equal to 0, you can see it will be like this. And now we are taking a vector such that by definition I'm taking its magnitude as unity or 1. Okay. So that will straight away help you understand one thing, that if
So
I
can you
place,
repeat what you said? My Wi-Fi was disconnected.
yeah, I'm saying it again. Okay, so if this is my vector A such that its magnitude is 1, but here I've placed it at what kind of angle? 0. So you can see that when a magnitude of a vector is 1, then its x component is how much? Cos theta, and its y component is how much? Sin theta. So here
Yes, sir.
directly you can see why cos 0 is 1, because the x component of this vector when it's at theta equal to 0 will be 1, whereas the y component will be 0. You can see. Okay, whereas for example, if you place the same vector at a position like this now, if I rotate the same vector and place it here now, where it's at theta equal to pi by 6, that is 30 degrees. Now its x and y component will change. It will become such that cos pi by 6, okay, that will be root 3 by 2, and sin pi by 6 will be equal to 1 by 2. Now likewise, if I continue this, and now I compare situation when I've turned this vector, let's say, to a position where is
Sir,
now
why
making
are
an
you
angle of,
making circles?
a circle is just to help you understand that we are rotating it, right? So the tip of the vector will describe a circle now, as we change theta. Understood? No?
Okay.
Okay, so now if we keep it at theta equal to pi by 3, pi by 3 is the same thing as 60 degrees. Okay. Then now you can see that it's the base which has become shorter and the perpendicular which is longer. Whereas here at pi by 6, it was the other way around. The base was longer and the perpendicular was shorter. So now cos pi by 6, sorry, cos pi by 3 has become half, and sin pi by 3 has become root 3 by 2. Whereas by the time I rotate it to 90 degrees, you can see it's the other way around now. It's exactly the inverse of what it was when it was at 0. When I keep it at the 90-degree position, then it's the y component which is equal to unity. So for theta equal to 90 degrees, you can see, or pi by 2, okay, cos pi by 2, that is the base for this one, that will be 0, or the x component of this one will be 0 when it's at the 90-degree position, whereas the y component will be equal to the vector's magnitude itself, which is equal to 1. Okay. So you can, so from this you can visualize why the trend of sin x and cos x between 0 and pi by 2 is the way we draw it. Okay. That is if you trace the base of this, or if you trace the x component of this vector, as we are changing it from 0 to 30 to 60 to 90, you can see what is happening to the x component. It's changing from 1 to root 3 by 2 in this diagram. When it becomes 60, it becomes half, to finally 0 by the time it becomes 90. So if you see the behavior of cos theta versus theta, you can see it's like this. It's going like this. By the time we come to 90 degrees, it's becoming 0. It is started from 1. So when we were at 30 degrees or pi by 6, it was root 3 by 2. When we were at 60 degrees or pi by 3, it's half. And by the time you come to 90, you can see that here cos 90 has become 0. Okay. Whereas if we see the sine function is having a kind of inverse of this relation. When theta was 0, you can see sine, that is the y component, was 0. Whereas by the time theta has become pi by 2, the y component of that green colored vector here is maximum. It's equal to 1. So if you compare the two, now you can see the graph of sine theta versus theta. It has the opposite behavior. It's going like this. At 0, it was 0. At pi by 6, it's half.
So here it is increasing, no?
Yes.
Oh.
So you can see that. Now you can see the y component. As your vector is rotating like this, you can see the y projection is increasing. So that's what's happening to sine theta. But at the same time, as your vector is rotating like this, your x component, what's happening? It's decreasing. That's what's happening to cos theta. So you can visualize that. So this is not just useful for this, but we'll also see what happens in the second quadrant now. Now, the moment my theta becomes more than 90, this vector is rotated to the second quadrant. So we'll see what happens to sine and cos next. Okay.
That
But
would
we
be
can
right.
take a note of this first. So this is another way to visualize how the values of the two operators, sine theta and cos theta, are changing as theta is changing from 0 to 90. Okay. I have not plotted the 45-degree point, but you can visualize that also. 45 is in between pi by 6 and pi by 3, or between 30 and 60. And that is the point where both of them will have a value of 1 by root 2. Sine theta and cos theta will both have a magnitude of 1 by root 2. So to understand what is happening to the cos theta graph, just visualize what's happening to the x component of that vector as I'm making it rotate from 0 to 90. The x component, or the shadow on the x-axis, that is decreasing from 1 to 0. And to understand what's happening to the sine theta graph, just visualize what's happening to the y component. So as I'm rotating it from 0 to 90, the y component is increasing from 0 to 1. So you can see why they have a sort of inverse behavior of each other, sine and cos.
Done, sir.
Okay, so people, this explanation is clear up to here.
Yes, sir.
Yes,
Okay,
sir.
so now let's move on to the second quadrant. Okay. So let's see what will happen when we rotate that vector to an angle which is obtuse, more than 90 but less than 180, or between pi by 2 and pi. So this is our y-axis, this is our x-axis. Now supposing what we have done is we have taken that vector of magnitude unity, and as we were increasing the angle by which we rotated it, we took it all the way to some theta, which has become like this now. So theta is greater than pi by 2. Less than pi, or greater than 90 degrees, less than 180 degrees. So it's second quadrant. So immediately what we notice is something very interesting, that this vector of magnitude 1, when we drop a perpendicular on the x-axis, it's on which side? It's on the negative side. So we can immediately see that our x component should be negative, whereas our y component, that will be positive because it's on the positive y-axis. Now you remember what was the x component of a vector of magnitude 1? It was nothing but cos theta. So immediately it tells us why cos theta has to become a negative quantity when theta is in the second quadrant, whereas sine theta will remain a positive quantity. So that's the logic for the ASTC rule. At second quadrant, sine is positive and cos is negative. You can see this is a negative quantity, whereas AY is a positive quantity. Okay. And not only that, now if you compare this particular theta, so if you compare this with another one in the, just a moment. Yeah, so if we compare this one, now in this, obviously this angle, let's say that is alpha. So alpha is equal to how much? It is 180 degrees minus theta, or in radians we'll say alpha is pi minus theta. Okay. Now if you compare this situation with one where our vector was in the first quadrant only, but with an angle of alpha, then you will see that the two situations that you are seeing here, they are symmetrical. So if this angle is alpha, then you will see that this and this should be identical. Actually, in a proper diagram, they should be identical. So you can see that in this case, this AX, which is cos theta, which is a negative quantity, It will be actually minus of cos alpha. Okay, because cos alpha would be this one, which is positive. So this one would be plus cos alpha, and this one would be sine alpha. So, and ay, which is sine theta, which is positive, would be positive of sine alpha. Okay, so now using this relation that alpha is 180 minus theta, so we can see we have the relation that cos theta is minus of cos 180 minus theta, whereas sine theta is positive of sine 180 minus theta when theta is in second quadrant. So an example of the application of this is that cos of 150 degrees is the same thing as minus cos 30 is minus root 3 by 2. But sine of 150 degrees is positive of sine 30. So that's half. Okay. So this is how it works in the second quadrant. And we will draw the graph also further of sine and cos, and further we'll understand this. So basically, the moment my theta goes beyond 90 degrees, you can see that this vector, the projection or the component it's casting on the x-axis is falling on the negative side. So cos theta has to be a negative quantity, whereas the projection on the y-axis is on the positive y-axis side. So the sine component is positive. Okay. And then if you take this angle, which is 180 minus theta, and you compare the vector in this position theta with respect to another vector when it was at the position of that alpha instead of theta, you will see that these two triangles here, this one, this triangle here and this triangle, they are congruent triangles. So they have the same magnitude of the perpendicular and the same magnitude of the base. But this one with proper sign, it has a negative ax, this has a positive ax. Both of them have a positive ay. So that is how we come to the conclusion that cos theta is minus of cos alpha with this one here, because the x components are in opposite direction, whereas sine theta is the same thing as sine alpha because the y components are in the same direction. So that's how we develop this formula for theta in the second quadrant, that cos of theta is minus cos 180 minus theta, whereas sine theta is positive of sine 180 minus theta.
Done, sir.
No, sir, please wait.
Yeah.
Done, sir.
Yeah. Okay, so coming back to this graph of sine and cos, now you can visualize further how the graph goes beyond pi by 2 or beyond 90 degrees. So for example, when we are in the acute angle region or the first quadrant, you can see that as theta is increasing, your base is decreasing. So cos theta, or basically your x component, is decreasing. So cos theta is decreasing from 1 to 0. And your sine theta, on the other hand, the y component is increasing from 0 to 1. But now visualize as the vector moves on to the second quadrant. Now when your theta becomes obtuse, so what's happening? So keep thinking of what's happening as your theta is increasing. So your vector strip is going from here like this. So you can see that the projection on the x-axis or the x component is again increasing from 0, but on the negative side. So it's going like this. It's going on the negative side and reaching -1 as you reach 180 degrees or pi. And it's going in a symmetrical manner. So symmetrical manner का meaning क्या हो गया यहाँ पे, that suppose we are at some value of alpha over here and we are at some value over here where this is basically 180 minus alpha. Then whatever this value, this will be negative of that much. So we have that relation that cos of 180 minus alpha is minus cos alpha. Like that. Whereas if you visualize what is happening in this rotation as, yeah,
So could you explain that purple part again?
what beta? I didn't catch you. A little bit louder, please.
Sir, could you please explain that purple part again? That obtuse
Achha,
angle.
okay. So see what is happening now. Now just visualize this vector now as it's rotating. So it went from 0. When it was 0, cos was 1, no? Because the x component was 1. So it went to some acute angle. So the base reduced a little like this. Okay. So by the time you reach 90, what is the base? It's 0. So cos has reached 0 value, right?
Yes, sir.
This much is clear, na?
Yes, sir.
Okay, now see what happens the moment you've gone beyond 90. The moment it's become an obtuse angle. Now what about the x component? It's gone to the negative side.
Yes, sir.
So on the graph, where should cos theta go? It should go on the negative side.
Sure.
Understood now?
Yes, sir. Thank you, sir.
And by the time you reach theta equal to 180, this is what has happened. Pi, this is only 1. Na? So the component has become -1. The x component has become -1. Okay.
Yes, sir.
So this part, this part is like a symmetric part to this part, but on the negative side. So it's like a mirror image on the negative side. Got it now?
Yes, sir.
Okay. Now similarly, see in this graph, what's happening to the sine function? The sine is the y component. So as your vector is rotating from theta equal to 0 to 90, the y component is going from 0 to 1. And then as you're going from 90 to 180, it's just coming down from 1 to 0. So this part is just going like this. The sine graph is coming back to 0 as you reach pi. So this has this kind of symmetry now, that if you're at some angle alpha here, the value of sine will repeat again at 180 minus alpha or pi minus alpha. So we have that formula that sine of pi minus alpha is positive of sine alpha. Okay, finished with this, people?
Yes, sir.
So now likewise.
Sir, 1 minute, sir.
No, sir.
Okay.
Done, sir.
None, sir.
Okay. So likewise, now we can see that as you move to the third or fourth quadrant, accordingly how sine and cos change sign and how they behave. Okay. So for example, in the third quadrant, the value of theta should be greater than 180 but less than 270. So it will be something like this. Okay. We are at like this. Theta is greater than 180 but less than 270. So now you can see that this will have a negative value of x projection or x component and a negative value of y also. So both sine and cos are negative in the third quadrant as well. So ax, which is cos theta, will be negative. Ay, which is sine theta, will also be negative. Okay. And in fact, now you can express this as, if you take this angle here as alpha, so you can express theta as 180 plus alpha or pi plus alpha, and therefore you can see that we'll get the formula that cos theta is minus cos alpha and sine theta is minus sine alpha. But this time alpha is equal to theta minus 180 or theta minus pi. So this formula becomes like this: cos theta is minus of cos theta minus 180 degrees. And sine theta is minus of sine theta minus 180 degrees. Okay, so this becomes the analysis for third quadrant. So as an example, you can see that cos of 225 degrees will be minus of cos 225 minus 180, so that's 45. It's minus 1 by 2. Similarly, if I have to calculate, let's say, sine of 217 degrees.
So this you're taking any value.
Yes, so we can take any value. No? So this is in third quadrant. So I'm taking between 180 and 270, right? So these
Okay, sir.
formulae will be applicable for third quadrant, right? So this will be minus of sine 217 minus 180. So that is minus sine 37. So that is minus 3 by 5. Okay. So this is how we calculate the value of sine and cos in third quadrant. And similarly, we can see in fourth quadrant. So just to complete off the four quadrants, you can see in fourth quadrant now. So one thing you should keep in mind is that we follow the right-handed convention. That means whenever we take theta as a positive angle, we are taking it as an anti-clockwise rotation. Okay? So positive of 270 means anti-clockwise of 270, and we should not take clockwise. Okay? So our convention is that anti-clockwise is taken as positive and clockwise is taken as negative. So anyway, in the fourth quadrant, as far as positive angle goes, it should be greater than 270 and less than 360, or greater than 3 pi by 2 but less than 2 pi in radians. Okay. So let's say we have something like this now. So this has been rotated by a theta, which is like this. You can see it's in fourth quadrant. So this can be expressed as, if this angle is alpha, so theta can be expressed as 360 minus alpha, or simply as minus alpha, because 360 is the same as 0. Okay. So anyhow, now you can see that for this vector, the x component is positive again. So in fourth quadrant, cos becomes positive, but the y component is negative. So in fourth quadrant, sine is negative. So ax will be positive. So that means cos of theta will be equal to positive of cos alpha. But ay will be negative, which means that sine of theta will be minus sine alpha. So from this we have the formula for the fourth quadrant, that cos of theta is is positive of cos 360 minus theta, whereas sine of theta is negative of sine 360 minus theta. Okay. So if we look at a similar example, let's take some angle in the fourth quadrant. So for example, 315 degrees is an example in the fourth quadrant. So cos of 315 will be positive of cos 360 minus 350. It will be positive of cos 45. So 1 by root 2. But sine of 315 will become negative of sine 360 minus 350. So that will be negative of sine 45. So that will be minus 1 by 2. Okay, so this is how we use the same concept for sine and cos in third and fourth quadrant now. Okay. And any angle which is more than 360, it just becomes a repetition of what we've done earlier. Like for example, if we have an angle of 390 degrees, 390, then it's the same thing as 360 plus 30. So 360 we are back to 0. So it's basically equivalent to 30. Okay. So that's how we can take trigonometric functions for any value of theta.
So
Yes.
in the last part, as you have written cos 315 degree, it should be in bracket 360 minus 45, right?
Sorry, it should be?
It should be 360 minus 45 and not
No,
315.
360 minus this thing. See, alpha is how much? Over here, na? See, alpha is 360 minus theta, no? Because theta plus alpha is 360, na? Got it, na?
Yes, sir.
So that's why.
Okay, sir.
So
Sir, sir,
Yes.
sir, in the end where you have written sine 315 degree, if we do it as sine 360 degree minus 45 degree, then to it will be same, right?
Yes. 315 is 360 minus 45, no?
Yeah, so in that way, if we write, then to it would be correct only, right?
But see, writing 315 as 360 minus 45 is not going to help directly, no? You're getting my
Sir,
point?
even if
It
we
should be
write,
minus of 360 minus, yeah.
acha, right, okay,
Got the
right.
point?
Got-
You have
Yeah,
to
got it.
get it as minus cos 45, minus sine 45, no?
Yeah,
You
got it.
understood, no? Hmm?
Yeah, got it.
Okay.
Thank you.
Okay.
Sir,
Okay, so this is clear, I hope?
sir,
Yes.
Only 1 minute.
Yeah, beta. What was
sir,
the question?
could you please show the graph of variation of cos and sine in third and fourth quadrants also?
Yeah, we'll come to the graphs also. But this
Okay.
formula is clear now from here, how we get the
Yes,
formula
sir.
for third. Okay. So this is the formula that you use for the third quadrant, right? And over here, this is the formula that we use for fourth quadrant. Okay. But what I'll also show you in the end that you don't need to memorize this formula. You can actually visualize this formula by this method of components. So given any angle, you instead of writing the formula on the side and trying to work plus minus from that, now you just make the diagram similar to this. And from that immediately you'll understand what value to take. Okay. However, let's first complete the
Sir,
graph.
I was writing 2 minutes.
Oh, sorry. My mistake. Yeah, finish it. No problem.
Sorry.
Sir,
Yes.
In that third quadrant and fourth quadrant, you draw a line in between. In that up, you something arrow and then what's positive, negative, what is it?
Sorry, Peter, which one in the third quadrant?
Sir,
This one?
so that
This angle
arrow
is
one
theta, no?
have what? Sir, your right side.
This is the theta, no? The arrow just shows the direction is anti-clockwise. Got it, no?
Sir, in that red marking I was asking here, right
This
side,
is
right side,
AX, is the X
right.
component.
Opposite of fourth quadrant, sir. Here. Sir, here.
This one here.
Sir, what you have?
This is just to show the sign convention that anti-clockwise is positive, right? And clockwise is negative. That's the right-handed system we follow, no? Got it, no?
Okay, sir.
Okay, so these formulae are clear now. Okay, so let's come back to the graph of sine and cos. Let's start with the graph of cos. We plot cos theta versus theta. Now just visualize, our vector rotating from 0 to 90, then 180 like this. So you'll realize that cos theta is the component on the x-axis. No? So it first decreased from 1 to 0. Okay. Then as we went second quadrant up to 180 degrees, it became -1. Okay. So this is pi. This is pi by 2. Now visualize further what happens in the third quadrant. So in the third quadrant, as we are going like this is our theta. So what is happening to the x component? It is reducing in magnitude, but it's going from -1. So by the time we come to 270 degrees or 3 pi by 2, it's come back to 0. It has this kind of shape. And then when we come to the fourth quadrant, so from here it's come to 0, and the x component has come to 0. Now when we come to the fourth quadrant, the x component has again become a positive value, you can see. Okay. So, and by the time we are back to theta equal to 360, it's become +1. So that's how the last quarter of this graph goes like this. So this is the graph of cos in one cycle of 360 degrees or 2 pi radians. So just visualize that vector going round and round like this, and visualize what's happening to its x component. So you can see that its x component starts from 1 when theta was 0. But as theta goes to 90, it comes to 0. Then as theta goes to 180, it goes to -1. Then as theta goes from 180 to 270, it comes back from -1 to 0. And finally, as it goes from 270 to 360, it comes back to 1. So that's your graph of cos theta in one cycle. And now once you have cleared 360 or 2 pi, you're back to the first quadrant. So it repeats itself. So as the vector keeps going round and round, your theta keeps increasing. This cycle keeps repeating itself because the projection on the x-axis or the x component, it keeps going from 1 to 0 to -1 to 0 to back to 1, and it keeps going back and forth like this. So the value of cos theta on the graph keeps going from 1 to -1 to 1 to -1. So it's like it continues in cycle like this. So keep continuing to infinity like that. Now similarly, when we visualize the sine theta graph, we have to look at the y component. Instead of the x component, we are looking at the y component. So this is our theta. Then this here is our sine theta, this line. Okay. So as theta starts from 0, sine theta starts from 0. So it goes from 0 to 1 as you reach 90 degrees. Then it drops from 1 to 0 as you again come to 180 degrees. Okay. Then as you go from 180 in the third quadrant, that's when sine theta becomes negative. Goes to -1 as you reach 3 pi by 2. And then final quadrant it comes back to 0. And likewise, it repeats itself after this. So from here onwards, it's a continuously repetitive graph like this.
So you have wrote 3 pi upon 2, no?
3 pi by 2, yeah. That's the same as 270.
Okay.
This point here is also 3 pi by 2. So on the x-axis, pi by 2 is the same as 90 degrees. Pi is the same as 180 degrees. Three pi by 2 is the same as 270 degrees, and 2 pi is the same as 180 degrees. So this is our quadrant 1, this region. This is our quadrant 2. This is our quadrant 3. This is our quadrant 4.
Sir,
Yes.
so beyond 2 pi, the graph keeps repeating, right?
Sorry, beyond 2 pi?
The graph keeps like repeating, right?
Yes, it will just repeat itself.
So,
That's
sir,
right.
where do we use the like values
I'll explain to
beyond
you.
2 pi?
I'll tell you. For example, when we come to a chapter like oscillation, now we will have something like this, that suppose the x coordinate of an oscillating particle behaves like this. It is sine of pi by 6 into t, where t is time in seconds. Okay. Now t is going to go beyond 12 seconds here. No? It's not just from 0 to 12 seconds. T might become
Yes,
14
sir.
seconds, 15 seconds. So then you can see this quantity inside this theta is going to become more than 2 pi. Na?
Yes, sir.
Okay. But practically, what about the value of x? It will still be restricted between -1 and +1 only.
Yes, sir.
So that's what showing that this particle, which is behaving like this, is oscillating between +1 and -1. It's never going beyond +1, never coming beyond -1 on the negative side. So that is
Yes,
a
sir.
practical understanding of how we might have to come across a situation where the theta for a sine function is going more than 2 pi.
Yes, sir. Thank you.
Oh.
That would be right. Sir, in this page, what all we have to note down?
Sorry, come again, beta.
Sir, I'm asking that in this page, what all we have to note down?
For this, what?
Sir, in this page, what all do we have to note down?
What all you don't have to note down anything because I'll send you the notes anyway. Na? You have to just understand how this graph came, from the concept of the 4 quadrants, right? More important is you understand what's happening. I'm sending you the notes anyway. So but yeah, what is important for you to remember is the nature of the cos graph, the nature of the sine graph, and all the formulae we have listed earlier, for the 4 quadrants. Got it now? Now see, let's just finalize this with, let's understand how we can use this practically in finding out values. So for example, if I just randomly ask you something like cos of, let's say, 225 degrees. Now you don't need to memorize any formula for this now. All you need to do is keep this diagram in mind. So 225 ka matlab kya ho gaya? It's 180 plus something, you can see. So that means I'm rotating my vector somewhere over here. If this angle is 225, okay, then you can see that how much is this angle? It's 45. Okay. So if this is of magnitude 1, then how much will be the x component? You can see that will be minus 1 by root 2. And how much will be the y component? That will also be minus 1 by root 2. Because if this is 45, you can see this. Okay, so you can see that 225 is 180 plus 45. Okay. So cos 225 will just become minus sine 45. Sorry, minus cos 45. In this case, it's the same, but just to be clear. So it's minus 1 by root 2. Whereas sine 225 is also minus sine of 45. It's also minus 1 by root. Okay. Now, if I ask you something a little bit trickier, like for example, what is sine of, let's say, 560 degrees? Okay. Now you might say, why to take something so complicated like 560 degrees? But suppose we just have something like this, okay, or 540 degrees, let's say. So
Nowhere in the
540, you can
quadrant.
see, yeah, it's which quadrant? It is 360 plus how much? 180, isn't it?
Yes, sir.
So that means what I'm doing actually, I'm rotating my vector by one full circle of 360 and then another 180. So where my vector is located? It's located here. It's located at 180. So you can see that sine of 540 will be the same thing as sine of 180, which will be 0. Whereas cos of 540 will be the same as cos of 180, which is basically minus 1. Because you can see that cos is the x component, which will be minus 1, and sine is the y component, which will be 0. Following this now, people?
Yes, sir.
So now, for example, if I tell you what is sine of minus 127 degrees. Okay. Now remember that minus means clockwise rotation. Okay. So you can just visualize it this way. You don't need to memorize any separate formula for this. So I'm now going clockwise through an angle of 127 degrees. So it should be somewhere here. This should be minus 127 degrees. Okay. So if this is 127, now you can tell me how much this angle will be. This will be 53. Right?
Yes.
So you can see that this will be actually in the third quadrant, where cos theta will be negative and sine theta will also be negative. Okay. And we will, from this diagram, you can see that sine of minus 127 will become minus sine 53, which you should remember is 4 by 5. So minus sine 53 will be this. Whereas cos of minus 127 will be minus cos 53, which will be minus 3 by 5. So you don't have to rely on any formulae and memorizing things and all. You can just keep whatever angle is given to you, you can just visualize it. Like if I give an angle now, like theta equal to, let's say, 5 pi by 3. Okay, so I want to find cos theta and sine theta. So just understand that 5 pi by 3 is actually equal to 2 pi minus pi by 3. Or basically it is 360 minus 60 or 300 degrees. So basically I'm talking about this kind of a rotation. Somewhere here, where this angle is 300 degrees or 5 pi by 3. So this angle is pi by 3 or 60 degrees. So you can see that the cos component is positive, the sine component is negative. So cos 5 pi by 3 will be equal to cos pi by 3, which is cos 60, which is equal to half. But sine of 5 pi by 3 will become minus sine pi by 3. So that will become minus root 3. So it will become like this. I'll just make this diagram a little bit more detailed. So we'll have to interpret this theta equal to 5 pi by 3 like this, or 300 degrees. That's the same as that. Okay. We'll have to interpret it like this, that we have rotated this like this. So that's the same thing as saying that this angle is pi by 3. You can see that the cos theta value is positive, whereas the sine theta value is negative. That's how I'm getting this one. Okay, so just make a note of these 2 or 3 examples here. Okay. Okay, so plenty of places in physics we'll see where we need to be able to quickly calculate sine and cos of various such angles, whether they are expressed in radians or in degrees. Okay, whether they are in first quadrant or fourth quadrant, or they might be even larger than 360, like this example of 540. So the best way to do this is with this visualization of rotating a vector of magnitude 1 by that angle theta. Okay, and from that quickly understanding which quadrant it is in. So therefore you can understand that x component is positive or negative, y component is positive or negative, and accordingly you can work out the formula quite easily. So ultimately, in terms of memorization, the only thing you have to remember is the 3 right angle triangles I told you. The 30, 60, 90 triangle, obvious isosceles right angle triangle, and the 53 degree, 37 degree, and 90 degree right angle triangle. If you remember the values of the ratios for those triangles, then you can relate almost any angle that will be thrown at you in a physics problem by just using this visualization. Okay, so this is a very important part. Okay, we will see in the next lecture how this becomes significant for our calculus part also. But right now you can treat it like general information, useful for vectors, useful for calculus, going to be useful in further chapters in physics. Okay. Especially students who are like not from the math stream over here. Those who are from the math stream, you have done this in trigonometry. So there's just another way of, another method of working out the same trigonometric formula that you've done. But especially for students from non-math stream over here, it's very important that you learn these methods. Okay, so that's it for today's class, people. Thanks for attending. We'll pick it up from here in the next lecture. Wish you all the best.
Thank you, sir.
Thank you, sir.
Have a good evening,
Thank you,
sir.
sir. Bye,
Yes,
sir.
people. Same to you. Have a good evening.
Thank you.
Thank you, sir. Bye, sir.
Okay, bye, people.